We talked about binomial probability distribution. So that's discrete. Okay, it either happens or it doesn't in terms of looking at successes or events that happen. Some things are continuous. The example, heights of students. So you can have a height, even if you can't measure to a certain, nearest 10,000, it's still possible to be a certain height, so it's a continuous variable. Here's another one. Time, obviously, is continuous. So Jack spends, the time Jack spends waiting for the LRT at Heritage Station after he arrives. So he doesn't know when the train is coming, right? But it's in 5-minute intervals. So you could calculate the probability of the time it takes for it to arrive. So it's continuous, because it can be any real number between 0 and 5. And it's random because he doesn't know the schedule. Obviously, if he knew it, he would always show up at approximately the same time. Another did ones like this back in Math 20 when you did normal distributions. Lifetime of light bulbs, so again, time, so it's continuous, but it follows a normal distribution. We didn't really talk about the function for a normal distribution, but that's actually the equation for it, if you ever wanted to know. Okay, so that's the equation for normal, obviously based on this particular example for the x values. So there's your mean, and in this case the standard deviation is 50. Again, you need to be told that in order to come up with the equation. So the probability is the area under the curve, just like we did for normal distribution. Now, it may not be a bell curve for our continuous probabilities, but it's still the area under the curve. If the integral is difficult, then maybe you need to use your calculator or a computer program to calculate the area. Okay, so that's an example of the first one. So here, this says use the probability function p of x and the integration function on the TI calculator to determine the probability that a randomly chosen light bulb will last between 825 and 875. So yes, it's a normal distribution, but we're going to do it practice using our calculator and the integration feature. And again, it kind of depends on how new your calculator is in terms of which one you're going to use, which feature. So first of all, if this was in a IB exam, show what you're entering in your calculator, show the integral, right? So we're going here, so this would be P from 825 less than or equal to x less than or equal to 875. And then 825, 875. And then look back up at your function. I'm just going to make my E just a little bit bigger here. Okay, so calculator, I got a better version here. So if you have a newer version, then if you go math, then I think this is new enough. You can go function integration. Basically, if it has the ability to print more than just a line, then you'll have that. Otherwise, you would graph that and find the integral of it. So here we can go from 825 up to 875. And then, and I would probably use the fraction feature just because it's, then you can kind of keep track of, you don't need as many brackets.
and then negative, and then I'm going to go fraction again. Bracket x minus 900. Okay. And then dx. Okay. And then we'll go to 3 digits, so 0.242. Okay.
Does everyone have that feature on their calculator? Okay. Good. Otherwise, as I said, you have to drop it and find the integral underneath. Now, for this one, because that is the equation of a normal distribution, you can use your normal distribution function in your distributions. Okay? And that's what we're going to do next here, right? So, normal CDF was used to determine probabilities that followed a normal distribution. So, in fact, that P of X is a normal distribution. So, here's your random variable X follows a normal distribution. Before we had B for binomial. This will be your mean. This will be your variance. We'll always show it as standard deviation squared. So that really is the standard deviation. So use that feature in your TI to determine the probability. So same thing here. So now this is going to be equal to normal. So normal CDF. And when we do that, so second distribution, it's the second one down. And it will, so again, depends on your calculator. So I have lower to upper. Some of you will have the ability to go to the, I don't know, left boundary, middle, or right, something like that. So you can ask me if you're not sure. So lower here is 825. Upper is 875. Mean for this was 900. And standard deviation is 50. Uh, 50 squared is the variance, right? So 50 is the standard deviation. So when you write this down, did it copy it out? Yeah, so here. So you put the left boundary, the right boundary, the mean, and standard deviation. If you want to write them out separately, that's fine. But if you put it in this, the left boundary, the right boundary, the mean, and the standard deviation. And that's what we used to have to do on the older versions of the calculator. We weren't prompted. So really you have to look up in a guide if you were first new at it to know what would happen. So same value, which was easier, normal CDF. Okay, so read the question. It says a normal distribution, then use your normal CDF. But make sure, again, IB wants to see everything, so state those values that you're putting in. Just don't write down the answer. Even if it says right, like show what you're entering in there, right? So they know, because it might be 2 marks, and you don't know where they're getting all their 2 marks from. All right? All right, so probability distribution functions that involve random variables are called probability density functions. Since there are many different probability density functions with many different equations, integration will have to be used to determine the probabilities, unless the calculator has something like a normal distribution, right? So properties, in order for a function to be a probability density function, of a continuous random variable, it must be non-negative, so basically positive, or 0. Sometimes it'll be 0 for a certain number of values, and then above that, and defined over the entire set of real numbers, even if the value over most of it is 0. So a lot of times it's going to be given as a piecewise function. Okay? And as well, total area under the function must be equal to 1. Otherwise, it's not a probability distribution. Okay? So there's the summary. So if you're going from negative infinity to positive infinity, the area underneath has to equal 1. F of x has to be greater than or equal to 0 for all real numbers. Probability that x lies in this interval is given by the area under the curve between those two values, a and b. Okay, so a definite interval. And just note here that if you're finding the area underneath between, so where the variable is greater than or equal to a, less than or equal to b, that's going to have the same value as if you didn't include a or b, okay? Because the probability at x equals a and the probability of x equals b are both 0. This is because the probability that a continuous random variable takes a single specific value is very, very small, okay? So even if there's a less than sign, you still include those boundaries, okay? Or greater than sign. So there's a probability density function. Notice how it's defined for all real values because this is the function for x greater than or equal to 1, less than or equal to 2, and it's 0 otherwise, okay? So that's okay. The function has to be greater than or equal to 0. And a lot of times part of it will be 0. So show that f of x has the properties of a probability distribution function. So really we want to make sure the total area under that curve for all real numbers is 1. Okay, so basically, so the area, so the integral, I should say, between negative infinity and 1, okay, the function is going to be 0, right? So that's obviously 0, as is the integral from 2 to positive infinity of 0 equals 0. So what we really want to check is probability of x between 1 and 2 of 2/3 x. Okay, and see what that is. So the total of those three has to equal 1. So now find the integral between 1 and 2. Do this one by hand, because you can do it pretty easily by hand. Okay, so then in B, find the probability from 1.5 to 2. So that's within that, this piece here. So we don't have to care about this, because 1.5 is within there. So write out that integral, but then you can use your graphing calculator. Okay.
I'm doing it the old way. Because my brain is old. Okay, there we go.
Okay, to 3 decimal places. Okay. Next one, given a different probability density function, we want to figure out what that k value is. So we don't know what it is, so that's the first step. What we do know is the area underneath has to equal 1. Obviously, in this part here, the area underneath is going to be 0. So we really only care about the top part. This we're going to do algebraically. So we want to have the integral from -1 to 1 of k times 1 plus x squared x has to equal 1. And then however you want it, if you want to expand it out or do it as is, totally up to you. So then using your calculator, so check 0.3 and 0.6, are they within this? Yeah. So we're going to use that function. So that's going to equal 0.3 to 0.6. Your k values 3/8. 1 plus x squared dx. And then enter that in your calculator. Oops. the next one, I'm gonna get you to show your work on it. Okay? Notice how this says the absolute value is less than or equal to 0.2. So that's equal to probability of x less than or equal to 0.2 greater than or equal to negative 0.2. Here. And let's just check this. Negative 0.2 is not in there, right? So we are going to go from 0.3 because the rest of it's, oh, sorry, it is. Looking at the wrong thing. Here's what it's defined for. So negative 0.2 is within here, so positive 0.2. So we'll just use that first function. We don't have to do the pieces of it. That was 3. So really, from there, you know how to integrate it. If you go back to that, it's going to be 3/8 x plus 3/8 divided by 3 is 1/8 x cubed. You can use your calculator, right? You're just showing the actual steps. Show that. And that's going to be just the negative of that, right? Okay, very similar in the next one. Is that mud? Like that's what they're like. What does that mean? How did everything turn on side? Very weird. Anyway. Okay, so the next one, very similar, calculating C. Just be aware that the actual values for this is for a company from many years ago because salaries have gone up. So with the salaries that you see here, it would be pretty tough to live on these days. Okay. So, this probability density function models the annual salary X in thousands of dollars paid to salespersons many years ago. Okay, so basically this means there's no one making less than $16,000 a year. Okay, this is 0. As I said, $16,000 a year, you can't really survive. So maybe if you think about it as salespeople in retail sales, part-time workers, that kind of thing. If you annualize the salary, then it kind of makes more sense. Because it is just for salespeople, it's not for the whole company with the executives and all that kind of stuff. So if you think about it that way, it's a little more reasonable. Okay, so same thing here. It's going to be 0 for this part. So we want to find, we know that the probability has to be 1 for the area underneath. So actually I'll start here. So this is going to be from 16 to infinity. C x to the negative 7 over 2 dx has to equal 1. So now there isn't a boundary on this, right? So doesn't say like the other one, or maybe the other one, did it say otherwise? Yeah, so that says otherwise. Yeah, it does say otherwise. So here, this part, this is not otherwise beyond this. This goes to infinity. It doesn't have 2 boundary points. So technically, we should really, for proper mathematical form, this is an improper integral. So going from 16 to t. Okay. And then take the integral. So that's going to be c x to the negative 5 over 2, negative 5 over 2. Space on that. Anyway, I'm writing kind of big as well. Okay, so really, you could take the limit right now if you want. As t goes to infinity, this is, oh, I put that in the wrong place. Oh, no, I didn't. Yeah, so that's going to infinity in the denominator, right? So that's going to make this go to 0. And then, is that a handout? No. And then here, this is going to be 2/5. Well, you can evaluate what that's. So 16 square rooted is 4 to the negative 5. Yeah. So 4 to the 5 in the denominator. Negative 2/5 c. And then that's going to be 1 over 1,024. So that's going to be negative. Oh, sorry, this should be positive because you're subtracting a negative. And then that's going to be 1 over 2,560 c equals 1. C is 2,560.
that on your calculator.
Okay, so then looking at median mode, expectation, and variance. So these will look similar. What is a bit different here? The median value, well, it's not really different, it makes sense. Median value splits your data in half. And you're just talking about any set of data. So same thing here. The area underneath is going to be a half. If you think of normal distribution, that's a bell curve. The median, mean, and mode are the same. That's what makes it a normal distribution, right? Because that highest value there, that middle point, that's the mean, median, and mode there. That's not going to be the same in any continuous, but for median, absolutely. The area underneath the curve to the left of the median has to be a half, and to the right of the median has to be a half. Doesn't mean it's going to be the same shape, okay? But that's, so the median value m is that value when you find the area from negative infinity to m, you get 0.5, or from m to negative, oh, that should be positive infinity, sorry, make that a positive. Should be 0.5. Okay, mode is the value of x where the function has a maximum value. And again, makes sense because really this curve comes from a probability histogram, right? The frequency is the highest at the highest bar. So that's the x value where the function has a maximum. So we can find that using derivatives, right? Expectation or mean is the area underneath the curve from negative infinity to positive infinity, x times f of x. So the data value times the probability, basically, at each value. And the variance, or the square of the standard deviation, is given, and these are just like we've looked at before. Most commonly, we end up using this one. We've already calculated the expected value. If we don't have this, well, that is this here, right? So we may have to calculate x squared times your function, right? So that's the same as that, that's the same as that. So rarely do we ever use this. Okay. So now this is the same example, now with that C value substituted in, 2,560. Determine the median salary for salespeople. Oops. So median, remember what we just said, that's when the area underneath is a half. Okay, so we now know here we're going to start at 16 and go to some median value. So from 16 to the median value, the half is 0.5. So algebraically solve that. and then round to the nearest whole dollar. I didn't put that in. Let's kind of simplify it.
Oh, not 28, 48.
Remember, these x values are in thousands, so take that answer and multiply by 1,000, and then round to the nearest dollar. And then the modal salary, so the mode of all the salaries, that's when you want to look at the x value at the maximum of the function. So take the function and take the derivative, set it equal to 0. Also, remember when you're looking at maximums, if there isn't a maximum there, it could be at an end point. So where are your end points there? You only really have one. 16 to infinity, right? But take a look at, it's kind of a hint to you. Okay, so there aren't any values of x that make that derivative 0. So then there's critical value when it's undefined, when x is 0. But again, that's not in your piecewise function. This is for 16 and above, so defined for 16 to infinity. So you want to check endpoints. So what's f of 16? This would be 2560 times 16 to the exponent negative 72. Okay, and so it is defined at 16, but if you think about your function, if you were to graph this here, so 2560 x to the exponent negative 7 over 2, and then your window from 16 to infinity, obviously, let's go to 50. Actually, you wouldn't even have that. You can hardly see it. So I don't need, because I started at 16. So let's change, if I change my window to start at 0. Okay, you can see here that that's starting at 0. So this function is decreasing. So the maximum is going to be at whatever that x value at the beginning is, which is 16. So the maximum, the modal salary most frequently is the highest one, right? So that's going to be 16 there. Okay. So if this function, say, had a curve that was increasing and then decreasing, then the mode will be at that x value where it's the highest. Think about these coming from like a frequency chart. Mode means the most frequently occurring, so where the function is the highest on your graph. So therefore the total salary is 16, again with 3 zeros, right? It's in the thousands. Okay, then the mean salary, take a look at the formula, it's x times f of x. And again, for what that's defined, that's from 16 to infinity for this particular example. So the mean is going to be integral from 16 to infinity of x times f of x. Technically, that's the limit as t goes to infinity of 16 to t, and this will be 2560x to the negative 5 over 2 dx. Then you take the integral of that.
that's obviously gonna go to 0, so we need to do that. And then here, this is gonna be 5120 over. We can just evaluate that. Okay, so that's the mean salary in dollars. It's going to be 26,667 if we round to the nearest dollar for these. So we'll be able to finish to D, and then you can work on example 6. I'll put it up tomorrow. Okay, so this one's variance. So remember, for variance, and it is in your data booklet, we can use this if we're given this, but we're not. We do know the mean. We just calculated it. So here, we'll go back and find the integral of x squared f of x. Okay. So, variance. And again, it's not going to go from negative infinity to positive in this case because of the 0. It's going to go from 16 to infinity of x squared times 2,560, x to the negative 7 over 2 dx. Okay, then minus. So what you might want to do is actually calculate this separately so you don't have to keep popping that out. And call this e of x squared. Okay. So that's 4 over 2, so it's going to be x to the negative 3 over 2. That's going to be negative, what's that, 5,120. And that's x to the negative 1/2 is the square root of x. Okay, so square root of t as t goes to infinity. That's still going to approach infinity, so that's going to go to 0. So let's be this over 4. So now that's going to be 1280 minus the mean squared, and that was 26.6 repeating squared. Keep it as exact as possible. You can convert it to a decimal. Go back up in your calculator, square that. Okay. Right, so that's based on, that's the value based on x being in $1,000. So actually, you just leave it like that.
So that gives you an example of each. Last example, 6 there. Weekly sales for a gas station. Again, functions given to you. Calculate the mean and the mode. You can do that on your own. I'll put it up tomorrow, but most of it at least. Okay? All right.